In this video, we will be talking about bar charts, pie charts, histograms, stem plots, and time plots. We can use these tools as a way of displaying data. We often use bar charts and pie charts to display categorical data, and we often use stem plots, time plots, and histograms for displaying quantitative data. Pie charts show the relative size of each value in relation to the whole. On the other hand, bar charts display the frequency on one axis and the values of the categorical variable on the other. You can think of bar charts as a way of tallying information. For quantitative data, we often use stem plots, histograms, and time plots to show information. We'll talk about histograms first. After collecting data from a population or sample, we can use a histogram to help us display the distribution of the data we collected. The frequency, or count, is displayed on one axis, and each count tells us how many data values fall within a predetermined interval on the other axis. This axis corresponds to the variable we have just measured. To read a histogram, you first pick one of the intervals and determine its height. So for the interval between 100 and 110, we see that the bar has a height of 8. This means that, from the data we collected, 8 people weigh between 100 and 110 pounds. For the next interval, we see that the bar has a height of 16, so this means that 16 out of the total people I collected data from weigh between 110 and 120 pounds. The rest of the histogram can be read in a similar fashion. A histogram is a form of a frequency distribution. Frequency distributions can be written in a table format, and they tell us how many data values fall within a certain interval. These intervals can be a little confusing. For example, if I recorded an individual's weight to be exactly 120 pounds, do I include them in this interval or this interval? By convention, we say that each interval does not include the right endpoint. So 120 is not included in this interval, and 130 is not included in the other interval. So in fact, 120 belongs to the second interval. Now you might be thinking, if the right interval isn't included, why don't I just rewrite my intervals like this? 110 to 119 and 120 to 129. Now the problem with this is that we don't have continuity. For example, if you weighed 119.7 pounds, there would be no interval that contains this value. Now a frequency distribution can be converted into something called a relative frequency distribution. The only difference between these two is that a regular frequency distribution shows a count, and a relative frequency distribution, as the name suggests, shows the relative frequency instead. It is called relative frequency because it represents the proportion of values in each interval in relation to the whole. To convert a frequency distribution into a relative frequency distribution, we will need to do some calculations. We start off by finding the total number of data values, and we do this by adding each frequency. We find that the total sum is equal to 50. Then, we will take each value and we will divide it by that sum. And as a result, we get the relative frequency values. To check if you have made the right conversions, you can add up all the proportions for each interval, and the sum should be equal to 1. The answer should be equal to 1 because we have used a ratio that relates our data to the total amount of data values. Because of this ratio, relative frequencies can be written in percentages. To convert to percentage form, all we do is multiply each value by 100%. In the same way, regular histograms can be converted into histograms that tell us the proportion of values for each interval. Now stem plots are like histograms, except they show each data point. Stem plots consist of stems and leaves. A leaf refers to the very last number, and a stem refers to all of the other numbers except the last number. Stems and leaves are usually separated by a line. For example, let's look at the number 117. The leaf is the last number, so this would be 7. The stem is all of the other numbers, so the stem is 11. On a stem plot, this would be written as so. Now let's look at the number 69. Using the same rules, we would get a leaf of 9 and a stem of 6. And on a stem plot, this would be written as so. Now when we have a string of leaves like this, it just means that I have the data points 30, 31, 32, 35, and 35. Notice how stem plots are constructed. Stems go down from low to high, and leaves extend outward from low to high. Depending on the dataset we are working with, sometimes we can get stem plots with too many leaves and we can get stem plots with too many stems. When this happens, we might not get a nice picture of the distribution, and as a result, we may not be able to get much information out of it. If we have a regular stem plot with too many leaves, we can convert it into something called a split stem plot. This conversion is called splitting the stems. To split the stems, we need to duplicate each stem. The first stem will run from 0 to 4, which corresponds to these values. And the second stem will run from 5 to 9, which corresponds to these values. The same logic can be applied to the rest of the stems. When we have too many stems, we can reduce the amount of stems by trimming the leaves. In this example, we have a very large dataset that goes from 201 all the way to 875. That's over 60 stems that we have to write. To trim the leaves, all we do is remove the very last digit. So notice for the number 201, the leaf is 1 and the stem is 20. After removing the very last digit, we get 20. So now the leaf becomes 0 and the stem is now 2. We would do the same process for each data value. By trimming the leaves, we get a better looking stem plot. Notice how we have reduced the amount of stems by doing this, and we have saved ourselves the trouble of having to write down over 60 stems. This is why trimming can be useful, but be careful when you read the stem plot after it has been trimmed. For example, for the top row, instead of reading it as 20, 20, 21, 22, 23, and so on, we read it as 200, 200, 210, 220, 230, and so on. This is because the original data was in the hundreds place. Now the last type of stem plot we will be looking at is called a back-to-back stem plot. Back-to-back stem plots are used to display and compare two distributions by using the same set of stems. So for example, we could compare data from males and females, or data from cats and dogs. Another way to display quantitative data is by using a time plot. Time plots show how a variable changes over time. By convention, time is always plotted on the x-axis, and the values of a variable are always plotted on the y-axis.